Okay, let's start. So, in today's lecture, we are going to continue our study about structural testing. So, this is today's outline. So, we will learn one more type of coverage, and we will learn some testing strategies based on this path. And we will also learn limitations of structural testing and have a quick introduction about data flow testing. But we won't go deep in data flow testing because it is covered in another course. So what we have learned so far for structural testing are some coverages like statement coverage, branch coverage, or condition coverage. And all these coverage criteria focus on specific or single elements of program structures. However, as we have seen during our practices or exercises, when we execute a program, we need to execute a sequence of these single elements. And that sequence of single elements will form a path on the control flow graph. As you can see here, when we execute the program, we can't really just execute one statement. If we want to execute the program, we have to execute multiple statements with one test. And there are some passes on this control flow graph. So this leads to a new criteria called path coverage. So the motivation of having this type of coverage is that when we are traversing through the control flow graph, we are actually combining different single elements of the program structures. And sometimes we need to have some kind of combinations of single elements to trigger bugs or failures. And path coverage actually requires that all the paths through the control flow graph are covered. And the definition of this coverage is defined as the number of executed paths divided by the number of total paths of the program. So consider this program. So this is the example program we used in our last lecture. So let's do a quick live poll. And I hope some of you are watching the live stream now, so we can have more participants for this. But let's try to do this. So there are many, as we can see, there are many different paths in this control flow graph. So how many test cases do we need to cover all paths for this control flow graph, for this example program? So remember in our last lecture, we mentioned that we can cover all the statements with only one test case. We can cover all the branches with only one test case. But what about path? How many test cases do we need here? Please do it, please do it. So a path is defined as a sequence of nodes and edges on this control flow graph. So how many test cases do we need to cover all the paths of this program? Two and 4. Actually, the correct answer is more than 4. The correct answer is it's actually much more than 4 test cases. Assume, because we have a loop here, we don't know how many times should we go through this loop. Because each time we go through the loop, we will have a new path. Because a path is considered as a sequence of executed nodes and edges. And whenever we execute the loop again, we will get a new path, because the path grows longer and longer. So we have to consider to somehow limit the loop here. So instead of using the maximum number of integers that could be taken by C programs, let's try to limit the loop to 100 times. This sounds quite reasonable, right? Because a list with 100 elements is not a big list. And the actual number in real-world cases could be much higher than this. So let's assume this loop, we limit the loop to 100 times. And how many paths could we get? So each time, so let's assume, so we get into the loop for 0 times. So how many paths could we have? 1 path. We just go through the fourth branch here. And that is only 1 path. And if we get into the loop once, how many paths can we get? Actually 2. Why? Because once we get into the loop here, we can get 1 path by going through the true branch, and we can get another one by going through the false branch. And then we get out of the loop. And that's the 2 test cases we can get by going through the loop once. And what if we go through the loop twice? What if we have 2 iterations for this loop? How many test cases do we have? 4. I think you are mentioning 4. Actually, we have 4 because we have 1 branch here. Every time we go through the loop, there will be 2 more chances, 2 times more chances, or 2 times more path. So in the end, if we limit the loop to 100 times, we will have 2 to the power of 100 paths. And that is this number here. And assume if we can run 1,000 tests per second, this will take this many years. And this is even longer than the existence of Earth. So this is actually infeasible for us to test all the paths of a program, especially when we have loops. So it's infeasible to achieve 100% of path coverage. So actually, theoretically, path coverage is the strongest coverage metric we could use for structural testing. But as we have just seen, it is infeasible in real-world cases, especially when there are loops. And this is not possible. It's not possible to achieve 100% of path coverage because of loops, because of even if we bound the number of loops, we can see that we still have a large number of test cases needed. So, but however, path coverage is an ideal case, and it is still useful if we can somehow use the characteristics of execution path without the cost of, if we can somehow extract information from the execution path. So we can somehow avoid the heavy cost here. So the way we do it is to use partitioning. So it's actually, the logic is quite similar to why we use partition for black box testing, because we have infinite space, or search space for input. And now we are faced with an almost infinite search space for execution path. And in order to deal with infinite search space, what we normally do is we do partitioning. So we can somehow partition the path or group the path of a program and make use of this partitioning to generate a reasonable amount of test cases. And therefore, this observation actually inspires us to have some strategies to generate test cases based on path. And the first type of coverage that is derived from path coverage is called boundary interior coverage. And remember, what we want is we want to partition the infinite number of paths into a limited number of categories. And what we can do is, since this infinite number of paths comes from loops, so we can somehow try to do this kind of partitioning according to the loop conditions, according to what happens with the loop here. So this type of boundary interior coverage actually groups paths that differ only in the subpaths they follow when they are repeating the body of loops. So inside the loop, there are multiple different branches, and we just, in this boundary interior coverage, we just care about each single subpath of a particular loop. And this may sound quite abstract, and but the motivation or the rationale is like this. So if we execute a loop multiple times, with the same path, it's essentially the same as executing the loop with repeating the loop just once, executing the same path. So this is the idea here, and let's have a quick look at a concrete example to show you how does it work actually. So remember, the definition is we try to generate test cases to cover the subpaths of a loop. So we don't care about what's happening outside the loops. So in this example, again, we have one loop here. And what we care is about all the subpaths inside this loop. So we don't need to care about what's happening outside the loop. We don't need to care about what's happening outside the loop. We just need to care about all the basic blocks within the loop. So how many test cases or how many subpaths do we have for this single loop? How many? And that's quite straightforward, actually. I believe you have answer in your mind, so you don't have to speak out. But the answer is 2. It's quite simple, because if we don't care about what's outside the loop, we only have 2 paths here. Divided by this if condition. So we only have 2 paths. So this time we only need 2 paths to achieve boundary interior coverage. And let's have a look at a more complex example. So in this example, we have a loop here, all the way going back to block B. So what are the subpaths of the loop? Let's go through all the potential paths one by one, starting from basic block B. So the simplest one is BM, and then we are not going back to B. So it is actually not part of the loop. And if let's try to go to the left branch first and go as deep as we can. And what we can do is we can have B, C, D, F, L, and B, back to B. And remember our strategy, we try to look for the leftmost branch and the deepest branch. So B, C, D, F, L. And the next one should be B, C, D, G, H, L. And going back. And the next one should be B, C, D, G, I, L, because we are going to check the deepest branch first. And this is the B, C, D, G, I, L, B. And another one is, since we have traversed all the branches after D, we can move to check the branches for C. And we can have B, C, E, G, H, L, B. And the last one should be B, C, E, G, I, L, B. So what kind of strategy have we used just now to get all these subpaths of the loop? What kind of searching strategy did we use just now? Yes. We are using a DFS, depth first searching strategy here. Actually, you can also use BFS here, breadth first. You can try it as a practice. I won't do it here. So, the other way we can actually traverse all the subpaths of a loop, and we can use test cases that can cover all these subpaths as test cases to achieve boundary interior coverage. And boundary interior coverage, as we can see, it can help us to remove the problem of infinite loop-based path. Note that this infinite is not really infinite, but it's just some kind of infeasibly large number of paths. However, the number of paths through this code could still be exponential, because whenever we encounter a branch within the loop, it doubles the number of paths most of the times if the branches are not interconnected. So they are doubling the number of branches. So we may need some additional limitations to limit the number of test cases we need. And this gives us another type of coverage, which is called loop boundary coverage. So this actually focuses on the problems related only to loops, not even within what happens inside the loop. We only care about the loops as an overall structure here. So it covers all the scenarios of how the loops might get executed. And for simple loops, so remember the term simple here, you will see what are simple loops. So for simple loops, which doesn't have a sub-loop, so what we can do is we can generate tests that will skip the loop entirely, which means that this test case will iterate through the loop for 0 times. And then we can generate a test case that takes exactly 1 pass through the loop. And then we can generate test cases that takes 2 or more paths through the loop. And optionally, we can choose an upper bound n, and we can generate test cases that passes through the loop for m times, where m is larger than 2 because we have already taken 2 as one of the previous test generation strategy. So where m is larger than 2 but smaller than n, and we can also test some values close to n. So did this remind you of something you have learned before? this one here, the strategy of designing the test cases. Does it remind you of something you have learned? No? Huh? Yes, yes. Actually, it's quite similar to boundary value testing. So actually, all the strategies or methodologies we have learned are somehow you will find that their basic logic are kind of interconnected to each other. So they are not like isolated concepts. So this is actually similar to boundary value testing, and that's why this type of coverage is called loop boundary coverage. So we are trying to cover some boundaries of execution times for loops. So this is called loop boundary coverage. And remember, we have this strategy only deals with simple loops, because there are many more complicated scenarios. So the first one is nested loop. So in this control flow graph, I intentionally changed the shape for these decision points to diamond shape to make it clearer. So you can see, and also I changed the colors. So you can see that there are two nested loops here. So the outer loop is related to B, the inner loop is related to F. So for each level of loop, we should execute or use similar strategies as what we have done for simple loops. And in addition, what we do is we try to test the innermost loop first, while keeping the outer loop executed for the minimum amount of times. And we move one loop. Once we have finished with the innermost loop, we move one loop out and keep the inner loop with those typical values we have used, or those boundary values we have used, and test that layer of loop. And we do this one by one until we have finished all the nested loops. So for example, what we can do here is, let's try to do the first step. So for this inner loop, in order to, we only care about what's happening inside the loops, so we don't need to care about E and A. And for this loop, for this inner loop, what we can do is we can try to test it for 0 times. So we are not entering the loop, which means that once we get to F, we directly get out to H, and then go back to B. So in this case, we are not entering the loop here. And what we can also do is, remember in our previous slide, we need to test, at least execute this loop once. So we need to get inside the loop F. We need to, there's a typo here. This should be FGH. We get inside the loop once, and then get back to FGH, and then get back to B. So this is the second test case we can have. And the third one, as you can remember, is we need to get inside the inner loop twice. So we need to repeat the process of FGH twice. And that gives our third test case. And let's don't do the optional testing. So we do it, we test it 0, 1, 2. 0, 1, 2. And then we can move on to the second step here, since we have finished testing the innermost loop. And what we can do is we need to generate, let's keep the typical value here. Let's say, let's keep the inner loop executed for 0 times. What we can do is we need to execute the outer loop maybe once. We need to execute the outer loop twice, and so on. and that's only for for 0 times, executing the inner loop 0 times. We need to also do it for 1 and 2 times here, if we have nested loops. And another situation, complicated situation, is concatenated loops. So there are sometimes in the programs there could be multiple loops connected with each other. And if the loops are independent, what we can do is we can just test them one by one using the strategy we have described for simple loops. And if they are interconnected, we use a similar strategy to the nested loop. So we start with the bottom loop and hold the higher loops executed for the minimum number of times, and then we work upwards all the way up. And actually all the way we deal with nested loops and concatenated loops, we use a bottom-up strategy here to keep things organized, to keep our design organized. So these are some basic variations for loop boundary testing. So you may wonder, why does this make sense for us? So why we choose to use these numbers like 0, 1, 2? Why do we use these 3 numbers here? Not just because they are the boundaries of the loop. There are some more reasons behind this. So remember if we want to fully verify, if we want to say a program is free from bugs, what we actually want to do is to use some kind of formal verification to prove that this program is free from bugs. And one of the important topics in formal verification is loop analysis. So we have to analyze whether, like the stopping criteria for this loop, like whether the loop is an infinite loop or not, things like that. And for loops, there are 3 different types of properties we need to check during the formal verification. The first one is called precondition. So preconditions are the program states before we enter the loop, like the values, the programs of the variables before we enter the loop. And we do have post conditions. And post conditions are the program states after we have exit the loop. And we also have loop invariants, which means that which are the expressions or conditions that should hold true no matter how many times we execute the loop. So those are called loop invariants. So we have these 3 important concepts when we do formal verification. And if we execute the loop 0 times, it means that the post conditions are true in advance. So it means that we are not entering the loop at all. So the post conditions after we have executed the loop should hold true even before we run it. So this is what we have tested if we run the loop 0 times. And if we run it only once, or if we run the loop many times, the loop invariant should always hold the value of true. So this is this is how we test for loop invariants. And since we are running this loop many times, or at least once, so we have the invariant and not loop condition will give us the post conditions. So the reason of having this not here is because we have to break the loop condition to get out of the loop to reach the post conditions. Actually, as you can see, our loop testing strategies, the choices about these numbers echoes these cases of how we verify or how we analyze preconditions, postconditions, or loop invariants. So this is why we use 0, 1, 2. So 1 and 2 helps with checking invariants, and 0 helps to check postconditions. So this is the rationale of why we use these numbers for loop testing. And there's actually another type of partitioning strategy other than using loops. So remember, in the program structure, we have some single elements like statements, like branches, and we can somehow combine them together to build a larger component. And this larger component could be named as a subpath of an execution. And the subpath is like a sequence of nodes and edges on the control flow graph without branching. So once we reach, so these are like the subpaths we can extract from one node ending at another node from the control flow graph. And each one of the subpaths here is called a linear code sequences and jump. So this is called LC-ICJ, and each one of them covers actually one linear segment of the control flow graph. Let's have a look at a concrete example here. So let's assume we have this. So I think you have missed what is LC-ICJ. So LC-ICJ is actually a sub-component of a control flow graph of program structures that are made by linear segments of the control flow graph, which means that each one of the LC-ICJ component doesn't have branches inside. So it's just a linear sequence of basic blocks we can execute. So for example, in this, and LC-ICJ is made up of these linear sequences and jumps or go-tos inside programs. So you can see in this program, because why we have go-to in programs is because when we write the program, we are like writing a sequence of statements, but these sequence of statements have structures. They can have jumps when we execute the program. So how does this happen? How can we convert a sequence of statements into a tree or graph-like structure? That's because we have go-tos. We can skip the execution of a chunk of code with go-to statements. So let's say, so that's why we have a jump here. If we don't jump in this condition here, we will just run through the chunk of code here. And similarly, we have a jump here. If we don't jump, the program will just go all the way down and go through this basic block naturally. So it's the same as the jump here, J3. We need to go back if some condition satisfies, and otherwise this program will just run through without going back. So let's have a look at some concrete examples here. So for for all these LC SAJ segments, we have a starting point, we have an end, and let's assume the starting point is entry B1, and the end is a jump at J1. So, what are the sequence of what is the sequence of basic blocks here? It's quite straightforward, right? It should be B1. So it should be B1, B2, and B3. Actually, the goTos are similar to the concepts of goTos in assembly code or C code. In C code, you can also have goTos. So that basically means if we don't care about goTos, the program will just run through. So we don't care. So for each one of the branch here, most of the time we only have one goTo because by default the program will execute one of the branches. And let's consider another one. So from entry to J2, what are the basic blocks? So it's quite straightforward. We just count out the basic blocks from entry to J2. And what are the next from and to we can choose from? We already have entry J1, entry J2. What's the next we can have? Entry J3. So it's also quite straightforward. And what else can we have? What else can we have? Because these are just segments of program structures. These are just segments of control flow graphs. So we may not start from the entry point. Because if we jump from J1 here, we are not taking the other branch. So what we can have is we can start from J1 to return. So we are like dissecting this entire control flow graph according to these jumps, according to these branches. So we can convert them into some linear segments. What we can do similarly here is, since we can dissect the control flow graph from J1, we can also do it for J2, and we can also do it for J3, and of course we can eventually get all the linear segments of this control flow graph. So this is LC-SAJ. So it's also about partitioning, but it's not related to loops. It's more related to jumps inside the programs. And LCG, for LC-SAJ coverage, it actually has an advantage. It allows us to set the sequence of LC-SAJ to have a length of n. And this length of n is because we can connect different small segments together. And this n here limits the number of segments we can connect in one test case, to build a test case. For example, if we set n to 1, which means that we are not connecting these segments together, that will give us statement coverage. That will give us statement coverage. And if we set it to be 2, it will give us branch coverage because we are connecting two segments together. We can connect them together. If they have overlapping nodes, we can connect them together. Then we can build branch coverage. And if we want to have path coverage, we need to have higher values of n. But we can't decide the number of n here unless we are given a particular program, because we don't know how many segments do we need to connect to build up the entire control flow graph. So we need to have higher values of n in order to achieve path coverage. As you can see here, this N actually gives us a flexibility to adjust the level of complexity when we deal with the coverage of program. So that's the advantage of having LC-SAJ. So that's the advantage of using this type of coverage. And let's do an exercise to practice what we have learned today. So first, we have learned boundary interior coverage. And can you try to generate the test cases for boundary interior coverage for this program? This is a search program, the same search program we have used for the exercise in our last lecture. And before we think about the test cases, we need to think about what are the subpaths we have for the loop. So how many loops do we have here? We only have one loop here. And how many subpaths do we have for this loop? Actually, only one loop, because this one goes out. This one is a return. So actually, we only have two here. I only have one here. So we don't really need to care about this one, because it's like a special node. It's an exit node. So when we do the testing here, we can either consider it as part of the loop. We can also ignore it. So this is a special case here for loops. And what about loop boundary coverage? So in loop boundary coverage, we care about how many times do we execute loops. So how should we design the test cases here? So we have a loop here. So we need to design test cases to run this loop 0 times, 1 time, or 2 times. So in this example here, is it possible to execute the loop 0 times? Let's do a live poll. Oh, we have a lot of yes, but we don't have no. Actually, the correct answer should be no. The correct answer should be no, because let's have a closer look at the program. So in the first basic block, we have index equal to 0. And in basic block 7, we check whether this index is smaller than n or not. And in order to reach this while loop here, we have to satisfy the condition that n is larger than 1. So if n is larger than 1, we have to get inside this loop anyways. We can't execute the loop 0 times with any test cases. In this case, in this example here. So as you can see, this example covers a lot of corner cases. So what about 1? Can we find a test case to execute this loop exactly once? Actually, the answer is also no, because index is initialized with the value of 0, and n has to be larger than 1, so n is at least 2. So we can't execute this one for one time. What we can get is we need to get inside the loop twice, at least 2 times, or maybe even 3 times. But that is a boundary value here. So this is what we can get eventually for this loop boundary testing. So that's all about the first half of today's lecture, and let's have a 10 minutes break. All right, let's start. Before we start the content for the second half, I did some quick updates for the slides to clarify some corner cases you may encounter when you do assignment 1. So you have to do boundary interior coverage for assignment 1, and there's a special case. So in this example here, we don't actually have a source code available for this program here. And the special case is the exit points of the loop. So if M is just an exit point without a correspondence to an actual code, then we can ignore it, and we can consider it as not a subpath of the loop. So this is really a boundary case. Otherwise, if it corresponds to maybe a return inside the while loop, then let's consider it as part of the subpath of the loop. So let's count it in if it is a return, or if it is a break or something like that within the loop. So with this modification, I hope if you are watching the recording, I hope you are not doubling the speed and you are not missing the details here. So for this, this will affect how we do this exercise. So since here, if we try to convert this control flow graph back into a piece of code, we can see that this return here should be within the block of this while loop. So let's consider this as part of the subpath. So what you have answered just now is correct. So we have two subpaths for this loop, because this exit point does have an actual piece of code related to it. So it's not just naturally exiting the loop. So it's not just a naturally ending of the loop. It is actually a piece of code within the loop. So let's consider this as one of the subpaths within the loop. Yeah, because sometimes an exit is just a natural exit without any code. And in that case, we can consider it not part of the subpath. But in this case, it has a return. And similarly, we can have go-tos also counted here. And maybe we have breaks also counted here. So, yeah. If the loop fails, then it means it exits naturally, right? So let's say this one here. If you convert this one into this one is like the loop fails. Let's imagine what the source code for this C program. It should have a curly bracket, a pair of curly brackets for this while loop, and this return is after the second curly bracket, is outside the code block for this loop. So it is considered not part of the subpath. So let's do this. Let's use this standard. And another update here is related to a question you have asked just now. So let's try to assume that we have reached BB7, because if we don't have this kind of restriction, we can actually exit here, we can exit here, we can exit here, so without exercising the loop. But let's try to assume that we need to reach BB7 in order to execute the loop 0 times. So because we are talking about executing the loop, which means that at least we are reaching this point. So let's have this assumption here. And this actually shows us that there are some infeasible paths in control flow graph, right? There are some infeasible paths, and there are some infeasible test cases, or some unreachable code. And this actually leads to our next topic today, the limitation of structural testing. sometimes, so no test can satisfy an obligation, just like what we have seen just now. If we want to execute the loop 0 times, we can never do that in real life for that particular program. And there are many different reasons for this. And one of them is what we have seen just now, impossible combinations of conditions. And to calculate, actually there are some methodologies for automatically calculating whether a condition could be satisfied or not. And that is called, there are some ICT solvers available around, and those are related to symbolic execution, but that is not part of the course. So, but at least you know that there is such a thing for you to automatically help you to check whether a combination of conditions could be satisfied or not. And there are some other scenarios that could lead to these kind of infeasible tests. So for example, there are some unreachable statements as part of the defensive programming. So defensive programming means that we try to program conservatively. We try to cover all the possible cases, even though some of the so-called possible cases may never appear in real life. So for example, we could have some kind of error handlings of code for conditions that can't actually happen in real life. So maybe for example, we can have an error handle. Let's say for the course registration program, we can set an error handling code for maybe if the cohort is larger than 10K students, then let's handle that error. But in reality, at least for CSE, we will never have 10K students for one course. So that is not happening in real life. So sometimes this could also lead to unreachable code. And there are sometimes we could have dead code in some legacy applications. So we could have some legacy code, and there are when we have a newer version of the code, some of the code are kind of becoming the dead code that will never be invoked or never reached again. So these are dead code. And there are some, of course, there are some inaccessible portions for the off-the-shelf systems. That code is actually related to a concept called reachability. So those are just some simple unreachable code. So or the code which are never used in the program. For example, you define a function, but you never use it, then it's considered as a dead code, and that function is never executed, so it's considered as dead code. And we can never build test cases, at least system-level test cases, to reach that function. So that's infeasible for testing. So normally how we address this infeasibility problem is that we can get back to the definition of adequacy. So we can use adequacy to score the test coverage we have already achieved. So for example, instead of trying to achieve 100% of coverage, we can set a threshold, maybe 95% of branch coverage or 80% of MCDC coverage is satisfiable. So once we have reached the threshold, we can consider that we have finished testing. However, this is not a satisfactory solution because different coverage could have different impacts on fault detection. So not every piece of covered code contribute equally to fault detection. For example, when you write your software, maybe you know that for some simple code, you may seldom make mistakes. But for some more complex logic, you may make mistakes. You are more likely to make mistakes. But if our, maybe let's say we have covered 80% of the code, 80% of the statements, but those 80% of statements are only the easier code, easier pieces of the code, then we are less likely to uncover bugs. But let's say if we have only achieved maybe 30% of statement coverage, but we are focusing on testing the more complex or more advanced logic of the code, then we are more likely to reveal bugs. So this is why simply using a threshold is not an ideal solution. The ideal solution here is to actually manually justify why each impossible, to manually justify the omitted impossible test obligations. And this is actually sometimes required for some very safety critical systems. But this is very time consuming, as you can imagine, and it's nearly as time consuming as doing a manual code review. So what industry or what companies does do in practice is that they will just stick to budget. So whenever they will stop testing whenever the money is used up or whenever the deadline is reached. So it's budget again. And before they actually when the companies do testings, they should have some testing plans, and when they do testing planning, they need to select techniques or select testing strategies they use. So in order to do this selection, we need to compare different strategies we have learned, and this is a comparison of all the different testing strategies we have learned. So as you can see, if we want to have the lower cost, we should do statement coverage, which is the most straightforward one, and path coverage is the most complicated or budget-consuming coverage metric. And sometimes boundary interior testing and compound condition coverage could be practically infeasible. But this is only can be impractical because in the previous example of the search program, remember, we could generate more test cases with loop boundary testing than boundary interior testing. So this is just in general, what's happening in general. And the reason of why boundary value testing could normally be more complex than loop boundary testing is because inside those loops we could have multiple if and else branches, and every if and else will double the number of subpaths inside the loop, and that normally leads to more test cases needed for executing the loop for, let's say, 0, 1, 2 times. So that's why it is more complex. And for ILC ICJ, it is normally simpler than loop boundaries because we don't need to care about how many times we execute the loop for ILC ICG if we can limit the number of n. So that's why ILC ICG could be costly, it could be less costly, and it could also be equal to statement coverage if we set n to 1. So this is also a special case. But other than that, this comparison can help to select the suitable testing strategy given the budget. So this is a comparison of what we have learned. And there are something more about the limitations of all these structural testing strategies. And remember, the motivation of using this type of coverage is that we cannot, using program structure coverage, the motivation of doing this is we cannot reveal an error if we never execute. We cannot reveal an error in a statement if we never execute that statement. But is the reverse true? So if we execute a statement, we can find errors in it. It's guaranteed to find errors in it if we execute through that statement. Is this true? If we execute a particular code or program structure, then we can definitely find error in it. Is this true or not? Actually, no. Let's see an example here. So, for example, the execution of a line or a piece of code structure doesn't guarantee to reveal the errors in that piece of code. Let's say we have a condition of A smaller than or equal to B. And let's say the programmer makes a typo. And the programmer types smaller than or equal to into larger than or equal to. And this is an error. And if the test case is written as A equals to B, then we can pass the condition here. We can pass the faulty condition here. We execute that condition, but we are not finding the error here. We are not finding the error here. So it behaves exactly the same as what was expected. So in this case, even if we execute the program, we cannot reveal the bug. So it is not just about we are reaching a particular part of the code. It's also about how we reach that part of the code. So merely executing code doesn't guarantee that we can find all bugs, even if sometimes we could achieve 100% of path coverage. We cannot guarantee that we can find all bugs. It's also about what inputs we choose. So it means that we need to care about values and data. So this is one of the conceptual limitations or the fundamental limitations of structural testing. So this is theoretical limitation. So if we use structural testing, we have to face with this type of limitation, and we can't deal with it with only structural testing. So that's why we need data flow testing. We need to think about the values and data. But for this course, as you can see here, we are only doing an intro here. That is because there's another course offered in UNSW to cover, and in that course, the major subject is data flow analysis. So we only do a brief intro of data flow analysis in this course, and this is to make your knowledge complete. You don't have to be able to use data flow analysis or do data flow testing after learning this course, but it's better if you can know these concepts and know, at least you know there's such a thing. And maybe one day in the future when you are doing some testing or when you are faced with these terms, you won't get lost. So remember, in control flow graph, we are viewing the program as a sequence of statements, and this sequence of statements controls how the program flows from one state to another. And we could have another view of the program, And the program could be viewed as a a sequence of program statements that can compute and transform values or transform data inside the memory of the computer. So this basically means that we can have a look at how the data or how the values are passed through this program according to the statements. So for data flow, we need to reason about data dependency. And if we see a variable is used in a statement, we can think about where does the value of this variable come from? Is it from another variable? Is it from somewhere else? We can also think about, given a variable, we can also think about, is this value ever used inside the program? And we can also think about, is this variable properly initialized? And this problem is actually, uninitialized variable is actually a problem with C programs. But from some more advanced programming languages, they don't have this error. They don't have this issue because the compiler will simply report errors if you have uninitialized variables. And for C, if a variable is not initialized and it is used, with some compilers, it may report you a warning, but it won't stop you from compiling. And if you don't initialize a variable, it will use whatever is inside the memory as its initial value, and this may cause some weird bugs. So we should think about whether a variable is properly initialized. And we can also think about if the expression assigned to the variable is changed, and if the expression gets changed, what will be affected by this change? So these are some interesting problems we want to address with data flow analysis. And there are many questions, or there are many interesting properties we want to know with data flow analysis. And again, like I said, this is a major subject. This is a very big topic, actually. And it is a major subject for another course. So as you can see, we are interested in so many different problems. How can we think about making it ever possible systematically? Because we want to do this, we want to do that, but we can't start with everything, right? We have to start with some smaller or more meta properties of the program. And the meta properties we use to approach this problem is called definition and use. So we care about definitions and uses of variables or values. So let's say a piece of data is defined. So it could be the scenarios of variables, declaring new variables and assigning values to this variable. And sometimes in some programming languages, it allows you to do the definition and value assignment with one statement. In some programming languages, you have to do it with two statements. For some older versions of C programming language, you have to separate the value declaration statement and value assignment statement. But I think I can't remember the exact version of C, but in newer versions of the programming languages, you can assign values to a variable once you have declared it. And the second thing we care about here is a piece of data is used. So this means that the variables are used to perform computations. And associations of definitions and use can capture the flow of information, the flow of values inside the program. And definition normally occurs when variables are declared, initialized, assigned values. So if we assign a new value to an existing variable, it is also considered as a new definition. Or receiving values as parameters is also considered as definition. And uses occurs in using the variables in expressions, conditional statements, passing parameters to a function, or the return statement. So returning a value is considered using that value. So let's have a look at an example here for definition and use. So in the first line, we have the definition of mean. And what happens for the second line is quite straightforward, right? Should be the definition of max and the use of n here, because we are assigning the value of n to max. So we define max and we use n. What about the third line? Definition of which variable? Mid and use of min and max. Yes. What about the fourth line here? It's actually a use of all these variables. What about the fifth line? What about the fifth line? Does it have any definition in the fifth line? Or it's only about uses? Fifth line. This one here. It's a tricky case. Just make a guess. Does it have? Yes? Okay, yes. Because remember what we just discussed, whenever we assign a new value to an existing variable, it is also considered as a new definition. So although mid was not declared here, it was declared in the third line, but it is assigned with a new value or potentially new value, then it is considered as a definition here. And of course, for the rest of the program, we have covered all the corner cases here. So for the rest of the programs, we can get all these definitions and uses. So let's continue. So in data flow analysis, what we care is not just some random definitions or uses. We care about def-use pairs. So what is called a def-use pair? So these are some requirements for constructing a def-use pair. So the first one is there is a definition of the variable at some location. And the second requirement is that, of course, because we have def now, we have to have use. So this variable has to be used in another location. And then note that the def and use must refer to the same variable. And then there is a control flow path exist from the two locations. So if there's no such a path, then it is not considered as a def-use pair. So although we are dealing with data flow, we have to use the control flow graph again, because if we just randomly pair things up, we will get a lot of infeasible or never reachable pairs. So that's why we need to follow the control flow graph path. And the path is definition clear for X, which means that there shouldn't be assignments value assignments to X in between the paths. So if there's a new assignment, then it means that there's a new def for this for X. We should split the path into two paths. So this is these are the requirements for building def use pairs. And let's come back to this example here. So what are the def use pairs for min? So first, we can see that min is defined in line 1. And the first use of min happens in the third line. So the first def use pair is 1 and 3. And what about the second def use pair? 1 and 4. And the third one, 1 and 5. And the first one, 1 and what? 6 is not min, it's mid. This is mid, not min. 1, 7. 7 is actually a def again, right? So it's actually 7, and if we follow the control flow graph, if we follow the execution path, 7 and which one? Which line? Yes, 7 and 4. And we still have one more, and that is 7 and 5, because we just follow the execution. So we should have these def use pairs. So although it is data flow analysis, we still need to follow the control flow graph. So we can get def use pairs, and there are a lot more advanced knowledge you need to learn if you want to do proper data flow analysis, because there are many more advanced problems like aliasing variables, because a lot of especially in C or Java, there are pointers, and we need to check whether the pointers are pointing to the same value or not to do data flow analysis. So there are a lot of more advanced analysis techniques for data flow. But we are not interested in that. We are interested in how can we derive test cases from these def use pairs. And because we are a testing course. So in order to build testing pairs, what about we introduce or what about we use the concept of coverage again? So what we can have here are all DU pair coverage or all DU path coverage. And we are using coverage again. So for all DU pair coverage, the name actually indicates how it is designed. So it requires each def use pair to be exercised at least once during the program execution. So we need to design a set of test cases that can execute each def use pair. And because def use pair are crafted based on control flow graph, so we must be able to find something to execute the DU pair. And this can actually help us to find bugs related to the def use statements. And remember, in the exercise we did before, by the end of the first half of today's lecture, we could see that we can easily achieve structural coverage without covering all DU pairs. So this means that we may miss out some failures if we only do structural testing, and this can help us to capture the missing vulnerabilities or missing bugs. And this coverage is defined as, again, the number of executed DU pairs and divided by the number of total DU pairs. And the second coverage here to be discussed is called all DU path coverage. Like indicated in the name, we care about path, execution path of DU pairs. And one DU pair actually may belong to many execution paths. So, because data flow and control flow graph are two different point of views, we can reach from one definition point to one use point through different paths. So what we need to do here is we need to cover all the simple paths at least once for every DU pair. This can help us to reveal this specific type of scenario. And the coverage is defined as this. But DU path coverage has, again, the path explosion problem. So we have experienced path explosion problem when we deal with loops in control flow graph. And here, again, we have to deal with path explosion problem. And this is because when we deal with path, even without loops here, the number of DU paths can be exponential to the size of the program. And when the code, especially when the code between definition and use is irrelevant to that variable but contains many control paths. For example, for this program here, so the DU for count could be the DU path for count for this count variable could be exponentially growing as we have more if conditions to check the value of the char here, because this is a bitwise AND. So because if we want to reach, this is a definition, this is use. If we want to reach this is also a definition. So if we want to reach the use here, we may need to go through a lot of if branches here. And whenever we reach a if branch, we have doubled the number of paths. So this will give us a path explosion problem even without ifs, even without loops. So that's a problem of using DU path coverage. And sometimes this is actually quite similar to how we deal with path coverage or path-related coverage criteria, like the boundary interior coverage. And that's the end of the main content today. And before we end, let's have a quick recap of what we have learned in the last 2 weeks, because they are mostly related to your assignment 1. And previously I was thinking about adding some MCQs in assignment 1, but eventually it turns out that they are too simple for large language models. Not for you, but for large language models. And since it's easy for large language models, then it must be easy for you, because you can use LLMs to do the assignment. And so I removed all the MCQs, and now you get only those text-based questions for your assignment 1. And don't rely on PyPy, don't rely on ChatGPT, because it may give you wrong answers. And let's have a quick recap of what we have learned for this during our last 2 weeks. So in the last 2 weeks, we have learned about black box testing and white box testing. And for black box testing, the most important challenge is that we have an infinite search space for the inputs. And in order to deal with this infinite search space, we use the strategy of partitioning. And we can do different types of partitioning. For example, we can use the boundary values in the requirements to do this partitioning. And that is called boundary value testing. And for boundary value testing, we have 2 different criteria for designing test cases. The first one is robustness. So we would like to test whether the program can handle invalid values properly or not. So we use robustness testing. And the second one is whether we need to care about the combinations of different we need to care about the assumption of only one fault. So if we have multiple parameters to test, we have to think about whether should we allow multiple parameters to take faulty values or not. So that will give us another dimension for designing the testing strategies. So in the end, because we have 2 dimensions, we have 4 different types of boundary value testing strategies. And another type of, because all the black box testing techniques are based on the idea of partitioning. So apart from using boundary values to do partitioning, we can also use equivalent classes to do partitioning. What we can do is we can extract equivalent classes that represents the same groups of inputs according to the requirement specifications to do this kind of partitioning. And again, it also has 2 dimensions, robustness and the assumption of only one fault is allowed. And after that, we learned some more black box testing techniques. We have learned some more black box testing techniques, including we have learned some more. Let me think about it. Other than black box, other than boundary value, other than equivalence class, we also learned decision table, which is more systematic. A more systematic approach. And in this approach, we care about the interleaving logic between different parameters or different use and effects of the program. So this is so decision table is actually the most systematic, considered the most systematic approach for doing black box testing. And for decision table based testing, it is quite costly, but it is also considered very comprehensive, and we also learned about the cause-effect graphing technique, which is inherited from hardware testing techniques, and that's all the techniques we have learned for black box testing. But apart from these important methodologies we learned during the lecture, we also have done a practice using randomsa to randomly test a program. And this kind of random testing is actually more generic than those methodologies we have learned, because for those methodologies we have learned, we have to derive test cases according to requirement specifications. And what if we just want a technique to test any program without manually checking those specifications? Then we just do random testing. But random testing is not purely random, as we have seen. It may try out some extreme values of the program according to those programming languages specifications. For example, we can try the minimum or maximum values of integers, of floats, of maybe long integers. So it is not purely random. And I hope you have tried that. And it is not part of the assessment, but it's good to try that out. And that's all the techniques we have learned for black box testing. And in this week, we learned about white box testing or structural testing. The reason of doing structural testing is that only using black box testing is often not enough to cover the internal structures of the program. So what we need to do is we need to collect information from the internal structures of the program to do the testing. So that's why the testing principle we use here is observability. We need to observe, we need to extract information. And this extracted information makes up the criteria we use to do white box testing. So all these but white box testing is more related to which criteria we use. And we have different levels of criteria. We have the simplest one called statement coverage. We can count the number of statements we have covered with our test cases. We can also have branch coverage, which are the edges on the control flow graph. We can also have condition coverage, which are all the conditions. And branch is only a special case of conditions, because branch are the conditions which are related to the control changing points in the control flow graph. And we also have path coverage. And because path coverage is really an ideal case, we cannot really achieve 100% of path coverage, especially when there are loops. So we have to do some, because we are facing infinity now, we need to do partition again. And with partitioning technique, since this infinity is from loop, so we mainly care about loops. And how do we deal with loops? Do partitioning with loops? We do boundary interior coverage, which is to calculate the subpath within a loop. And we also, another approach for dealing with loop is to limit the number of times that we execute a particular loop, and that is called loop boundary coverage. And remember, because it's also a boundary coverage, so it also inherits some of the ideas of boundary value testing. And apart from using loops to do this partition, we also have LCSAJ, which is to collect the linear segments of the control flow graph to do this partitioning. And after that, after we have learned all of these white box coverage criteria, we learned the limitation of these criteria. Sometimes, with the example, we could see that sometimes there are infeasible scenarios. There are some scenarios where we cannot get a feasible test case, and that's one of the limitations. And that's sometimes that's a limitation with regard of the implementation or the engineering, so-called engineering limitation. And a more theoretical limitation is that we can't only think about path. We can't only think about execution path. We have to think about. We can't only think about whether we could reach a particular piece of code or not. We should also think about how do we reach that piece of code. We have to think about the values, the data we use to reach that piece of code. And that's why we need data flow testing. And for data flow testing, we care most about def and use. And for def and use, we care about def-use pairs. And for def-use pairs, we need to rely on the control flow graph again, because it needs to be feasible. And for diffuse pairs, we have two different strategies for developing test cases, and that is to cover all the pairs or to cover all the paths between the pairs, between the def and use pairs. But of course, covering path will give us the path explosion problem again. And that's all of what we have learned in the past 2 weeks. And these are some basic methodologies for you to design test cases. It's not related to a particular programming language. It's not related to a particular tool you use. You can use whatever tool to do these kind of to design the test cases, and you can use whatever programming language to implement this. But this is more like the meta methodology for designing test cases. And in our next week, we will learn different levels of testings during development, and we will learn more concrete testing techniques that are less, that are not so theoretically fundamental techniques. So that's all about what we have learned this week. And assignment 1 is designed to check your understanding of these fundamental methodologies. So that's it for today. Thank you for coming.
She said that we don't have to actually hold the mic because I don't know how they do it. Well, let's check like an old recording and see if like under course hub, course info hub, my feedback stuff, lecture recordings. So September 19th. You already recorded. so you probably do. But is that the one with Mitko or let's see the previous one?
That time we started 2 weeks.
That's on the first day, yeah?